there's any injuries there. Wasn't able to tell if there's any injuries there. So, today we are going to talk about a form of metaprogramming. And I want to say right away that what we're going to talk about today is not going to be the. Here's a weird random function that doesn't take any parameters, but it's got a return type that's a type variable. And how do you do that? You can't specify that return type just by calling the function. But what you can do is you can bake it in different ways, right? This is not a very good random number generator. Don't use this at home. But we're taking a large value, cafe babe food face, right? And we're going to cast that value to the resulting type and return that as our random number, all right? So the first thing to note is, like I said, you can't call this function directly because it won't know what t is. So if I just try to call random like that, it'll say, polymorphic variable t is needed but was not specified on line 499. And by the way, on line 492, here's the procedure needing the variable. Okay, so that's very helpful. It gives you both the calling site and the site where the variable lives. But I can bake that for different types. So I can bake a random that returns an S32, right, a signed 32-bit number. I can bake a random that returns an unsigned 8-bit number. So now I'm just going to call those, and I'm going to print the result in decimal and hex, right, just so you can see it. And that's up here. A random of S32 gives me food face, or this negative number, right? And random of U8 gives me 206, or the CE, the SK at the end of food face. So that's cool. Hopefully that's clear how that works. So now we can bake something with multiple types to just show some more complicated cases. So I've got a named bake test where I've got A1 and A2 that are both of type A. I've got B1 and B2 that are both of type B, and I'm returning an A and a B. For the return value of A type, I'm going to sum A1 and A2. And for the second return value, I'm going to take the product of B1 and B2, right? So I'm returning A sum and B product. So I can bake that in different ways, right? So here I'm going to bake it with A being float and B being int, right? And then I'm going to call it down here. Sum is whatever, product is whatever. I'm passing it these literals that can implicitly cast to either int or float, right? That's the rule for literals. If you type a 4, that could be a float, right? So unless you specify that it's not. So here we go. We're printing sum and product, right? And sum is 3.0, product is 12 because we baked it with A is float and B is int, right? Now we can swap that, for example. B is float and A is int, and now we'll get oh no, because the printf expects them in the opposite order, so let's not do that. Right, that worked. It's just that the printf then is trying to print a decimal in this %f and a float in the %d, and that's bad news for both things. But it worked. So we can do this other thing, right? Note that we're baking with named arguments, so we can specify the arguments in any order, just like with regular function calls, as we saw last time. So we can bake with B is int and A is float, which is the same types we just baked, but I'm just specifying them differently, and that does what you would expect as well. Now we can have this weird function where there's no type on the outside at all. It's not there's no type variable in the arguments. There's no type variable in the returns. But internally, we're just doing something that uses some random type, right? And we can bake that. We can bake this function internal with some type as U64, and we're going to call it on 6000 and say, hey, that's 6000. And just like with before, we can't really call it directly. If we try to do that, it'll complain that some type is needed but was not specified, right? And there it is. Line 538 has some type. Okay. Now let's start getting to the, that was the intro. That's the intro. And now we're going to start getting to the kind of the really interesting feature that gives this language a lot of new things, or at least certainly things that I haven't seen before. All right. Here's modify. Now, so far, what I've just shown is, here's the basic mechanism for polymorphic functions in this language, equivalent to template functions in C++ or D or something. Now, a lot of languages that have type variables and polymorphic functions then start layering on things in the language to help you deal with the complexity of that, right? Like in C++, for example, there's this proposal called concepts that's about trying to make error messages easier to catch, or trying to make code more self-documenting, that's about describing what the parameters to a polymorphic function could be. I don't like that approach, because you start layering this declarative language on top of your imperative language, and you're making the language more and more complicated. So just like in that first demo where I said, hey, compile time execution lets you do all this awesome stuff, now the philosophy for the rest of this demo is going to be to leverage compile time execution to the greatest extent possible in a way that other languages don't do. And that gives us a great degree of amplified power over these generic template polymorphic functions, right? So now let's start looking at that. So we're going to look at this thing called a modify directive. And what that is you can attach it onto a polymorphic procedure, right? And it supplies code that runs at compile time that maps the types given by the user onto the types of the generated function, right? Prior till now, anytime we had a polymorphic function, the type of the resulting function that gets compiled was whatever the exact type happened to be at the calling site, right? And now what the modify directive is it takes a function that can modify that type and turn it into a different type. And to do that, we're going to use the runtime type information that we provided earlier. And if you didn't see that demo, it's a couple demos ago. You can find it on YouTube. But basically, we have these type info structures that are generated by the compiler and put into a global table, and we can use them to reason about types, right? Now, here we're not going to do that at runtime. We're going to do it at compile time, but it's the same mechanism, and it's very powerful. So as our first test, we're going to be very boring. We're going to take some variable a that's of any type, I don't know, right? And not an any type, which is a different thing we demoed. This is of arbitrary type. It's anything that you could pass. And then we're going to modify it by this function that takes that type t as a pointer to a type info and returns whatever it wants. And it's going to ignore the initial value of t and say, you know what, the type of this parameter should be a signed 64-bit number, right? So now we're going to call it with an int and an unsigned 8 and a signed 64, just like we did at the beginning of this demo. But what this modify is going to do is override all those choices. So in here, we're printfing the value of a, and the size of a is some number of bits, right? And then we're going to print the pointer value of this type info so that we can verify that it's the same every time, right? Now, to tell you the size in bits, we're going to cast the type info to a type info integer, which would be a dangerous thing to do usually, but we know down here we're only calling it with int, so it's fine. And then we're going to look at this field size in bits that's on that type info, right? And what we see when we run this, hopefully I did everything right. Here we go. Value of a is 5, but the size is 64 bits, and here's the pointer to the type info, right? Value of a is 4, but the size is 64 bits, and the value is minus whatever, but the size is 64 bits. And here's the type info every time. So that's interesting, right? We've obviously got control over what gets generated here. Now, this is a very trivial case. But we're going to start building it into more and more complex things. So now, just to show you that that's working, I'm going to turn off this modify directive, but just by commenting it out. So now we've just got a regular function test, just like we did through all those examples, right? And now if I run this again, you'll see the first one's 32 bits, the second one's 8 bits, the third one is 64 bits, just like you would expect, right? So obviously, oh, and the type info pointers are all different because those arguments are different types. So it's still a polymorphic function, it's just this modify is overriding it to do the same thing every time we call it. But we can do things that are more interesting than that, okay? So remember that random function that we couldn't call directly because the return value is only specified here, so we were baking it before. It's still got Cafe Babe food face and is still casting that to some type t. But now we're providing a modify function, and it's saying, well, if t is null, which is what happens when this type wasn't specified, then let's just say we're making a signed 32-bit random function, right? Or a random number, right? Otherwise, return whatever type was specified. So we can now call it, we couldn't do this before, right? But now we can call it directly, and by default we'll get a random that gives us a signed 32-bit number, right? Which is that stuff. And just like before, we can bake it to U8 and call it, right? So now we've got a very versatile function. We can call it, or we can specify what we want and call the specified version. So that's cool. And just to show that that's doing stuff, here let's change the default value to U16 instead of S32, and we'll run it again. And there we go. We have an unsigned 16-bit number instead of a signed 32-bit number, right? So that's great. Let's go back to our sum example, right? Remember last time I summed together all these elements of an array. But now I want to be more careful about what I'm doing. Because remember, when we summed the array of 8-bit elements, if you returned an 8-bit element, you're going to overflow very easily. I want to avoid that. But I also want my sum function to work on all kinds of types. So here's what I'm going to do. I'm going to return a different type. So now I'm taking an array of T, but I'm returning an R. What's R? We'll find out, right? You can't specify this by calling, so our modify proc has to specify it. And what does it do? Well, it takes T and R as arguments, and it returns two return values. And first of all, we're going to say, hey, if T is not an integer, then just return whatever T was, both for T and R. So, for example, if you call sum on an array of float 32s, then float 32 is fine. We're just going to sum up a bunch of float 32s, and that's great. Floats have enough precision. We're only worried about integers. So right away, this sum will work for any float type and do exactly what the previous sum did because we're not monkeying with the types. Okay, down here we know it's an integer, so let's look at the type info, size in bits. If it's a 32-bit integer or greater, signed or unsigned, we're not specifying, then again, return the same type for both T and R, right? So if it's big enough, for the purposes of however we're going to use this function, we've decided 32 bits is big enough, so just do whatever, right? But suppose you passed it a smaller number than that, like 16 or 8 bits, then we want to return, let's say 32 bits. We always want to make sure it's at least 32 bits. But if you gave us an array of signed things, we'll give you a signed 32-bit. And if you gave us an array of unsigned things, we'll give you an unsigned 32-bit, right? So if it's signed, return, we always return T in all these cases, right? Because it's an array of T. You don't want to monkey with that. But our return type is going to be either signed 32 or unsigned 32, depending on what the type of the element of the array was. That is a very specific thing that we just did and very complicated. And if you're trying to do that in a declarative way, it's going to get messy and going to require this big meta system with all these different ways of saying things. But we just leverage the programming language that we already have to do this very complicated thing, right? So now here's the actual body of sum. Once again, we just got a result. We say for A, add it to the result, and then return result, right? So now down here, we've got 3 arrays of different types. They're starting uninitialized, which is what that means, if you recall that from a very early demo. We're filling the arrays with, at every index, we're putting that index times 10, but of different types, right? So the first array is going to be float 64s, U16s, and S8s. We're going to sum them all, and we're going to print the sums, and that's what we get here, 450 for all 3 of these. Now, notice that this is really working because 450 is not storable in 8 bits, right? But our third array is an array of signed 8-bit numbers. So obviously the return type for C is bigger than 8 bits, right? Whereas before that would have failed. Now our modify proc has made it succeed. So that is, to my mind, a very powerful thing. And I'm going to take 1 second and eat a bite of cupcake before going on because I'm getting hungry. Pardon me. This is the advantage of doing a demo from home rather than at a conference. So while I was eating that cupcake, Tyler made a point in the chat that I just happened to see. There's probably been lots of good comments in the chat, but I can't read them all right now. But I happened to see Tyler's comment, which I thought was great. He said, hey, it's hard to call it metaprogramming when all you're doing is regular programming at compile time. But that's the point. Metaprogramming, as you would stereotypically think of it, is hard to think about. It's hard to reason about because you've got this meta thing that's separate from your regular thing, and who knows what's going on, right? And the point here is that we're bringing the meta as close to what you regularly do as possible. So it's just normal stuff that you're used to thinking about, that you're used to being very effective in, right? And let's bring that effectivity over to what is normally considered the meta part. So that's what we're doing. We're trying to make metaprogramming as boring and normal as regular programming because the exciting part should be what you're doing, right? It should be the task you're accomplishing, not, language complications, right? We want the language to be as simple as possible, but no simpler, to use that old chestnut. Okay. Now, probably some other people were saying this in the comments, this starts to get hard to read because we've got this sum function, but then we've dropped this giant modify function in there. And you know what? It's dwarfing the original function. And depending on what we want to do in here, it could get more and more complex. Also, maybe we want to share this modify code. If we're doing an operation commonly, we want to share that among many things. So as it happens, this doesn't have to be specified right here, right? You can refer to it by name somewhere else. And so down here, we've pasted exactly the same thing. So here's our sum function, but we've given a modify proc by name, ensure r is big enough. And we've done ensure r is big enough here. And we've taken a little more care. Now that it's separate, I've made the function even a little bit bigger, right? So first I check if it's specifically float, then we document what we're doing. We like float 32 and float 64. Then we say, hey, if it's not integer, let's do a printf that complains. At some point, we might have an API function for officially registering a complaint or an error from your compile time functions, but right now I'm lazy, so I just printf, right? So here's a printf, and I just try to explain what's going on. Like, look, the modify proc ensure r is big enough only takes integer float types, and then I have an official way of telling the compiler that I do not accept what you're trying to do, which is returning null for any return value. So anytime I return null for a return value, the compiler will register that as a complaint and give you an error message, and we'll see that in a second. Then I do the same thing we did before. Let's look at type info integer. If it's greater than or equal to 32 bits, we return it. Otherwise, we do different things on signed and unsigned, right? So first, let's look at the regular use. We're using that in the same way, except we're doing something a little more meta here. But for now, let's ignore that. We're just filling these up and summing them. And that's this second 450s, right? The first 450s was our previous test. This one is this one. So now, just again to prove that that works no matter what, let's put ensure r is big enough at the end of the file, and it still works, right? Let's put it into some file called far away, and it still works. So again, I don't remember how to pop the cut buffer in Emacs, so I'm like, yeah. I have a very reduced instruction set attitude toward Emacs. So just like everything in the language works hard to make sure you can do all this stuff with the code organization that you want. So this ensure r is big enough or whatever. This is a toy example that isn't really what you would do in reality, but there could be a part of a library of functions somewhere that you're commonly using as part of a toolkit by name, and it just works. All right, so let's give an example of returning null. So instead of, so here we've said, hey, if info is signed, return S32. Instead of returning unsigned, let's complain. Let's say, you know what, I don't want to accept unsigned types. I'm going to reject this polymorph. And then we return null for t. So there we go. That happens. And it tells us, line 679, a modify proc, return null for value 1. What's 679? That's the header of this modify proc, right? And it says it's in response to a polymorph cause here at line 741, which is result B, right? Because result B has the U16. U16 is an unsigned 16-bit number, right? So again, the error message is helpful. It is helpful. Yeah, am I deleting the right thing? Yes. All right. So now let's make the point that we actually did this instead of manually writing loops to iterate and fill the arrays like we did last time. We're actually calling a function fill in sum on the array that also does modify ensure r is big enough, fills the array, and returns sum of a, right? So we're using this function twice. That's useful. And we've got a 2-level nested polymorphic function. And so actually, when I got this error message a second ago, that was helpful, right? That actually happened 2 levels down. Or no, actually, never mind. That happened 1 level down because it happened in this ensure r is big enough. But, or no, it happened in the other one because it pulled this. Oh, right. Okay. Yeah. Anyway, so we do all that. Now, so far I've only been showing one modify routine at a time, but you can chain them together, and if you use more than one, they get called in order. So like I said, you can have a toolkit of them that you just apply. So here I've made another one called reject r if float, right? We're only going to look at r this time. We don't care about t. And if it's a float, just return null. And I'm not going to bother explaining why. That's your problem. And if it's not a float, we'll fall through and return r. So now I've got fill in sum 2. And I'm going to first ensure r is big enough, but then I'm going to reject if float. And for array B and C, it'll work fine because those were integer arrays. But A, remember, was an array of float 64. So right now, this is running fine. But if I comment out this one, then my reject r if float will complain, right? At line 759, this modify proc, reject r if float, return null. In response to a polymorph at line 773, right? So that is useful. That's 2 of them chained together. Now, let's do something even more interesting. So far, we've just been doing polymorphic stuff on numbers, but we can do them on anything. Let's do them on class hierarchies, right? And one thing that can happen in a language like C++ is you have some function that wants to do something. Like say you've got a game and you've got this entity hierarchy where you can have an entity. Actually, let's talk about specifically what I do here. I have an entity, right? And I have a human, which is using entity, right? So if you missed using, that's in an earlier demo. The way I'm using it here is it's like subclassing in C++, but it's more versatile. So I'm basically including entity in this human struct, so human is kind of like a subclass of entity, and then I've got some additional property. And I've got a royal, which is a human, and then it's got this additional stuff. But then I've also got a peasant, which is also a human but has smelliness. And interestingly, I'm putting the smelliness first in the peasant because the smelliness always comes first, which means his offset of his human is going to be different than the royal's offset of his human, which will matter interestingly in a bit. So if I'm calling a polymorphic function on these guys, what might happen, especially because these humans are at different offsets, is that you get different code generated for an entity, and an entity human, and an entity royal, and an entity peasant. You might get 4 of the same freaking function, even if all you're doing is editing the position, right? And even if you deduplicate at the code level, this is going to fail that deduplication, right? Because the human's at a different offset. That'll fool it. So what do? Well, you could, since we are only going to, I'll show you the code that we're actually going to do. We're just going to print position xy like we did before with a label at some string, and then some entity or other thing, right? To complicate it, we're actually going to apply this also, in addition to these entities, to a totally different class hierarchy. That's why we have a polymorphic function, right? We've got a screen rectangle that's got a vector 2 position instead of a vector 3 spatial position for entity. And we've got a textured rectangle, which is like a screen rectangle, but also has a texture map and a scale color ARGB, right? So we can call print position xy on any of these things, which gives us a sort of a duck typing, right? Because we don't care what thing is. All we care is that we can say, you know, thing.position.x and thing.position.y. Anything that satisfies that, we can pass to print position xy. So we only care about position, though, which means if we're given an entity royal, we really only want the entity, because that's where the position lives. And if we're given a textured rect, we really only want the screen rect. That's where the position lives. So in order to reduce code bloat, right, and reduce compile times of generating the same function all these times, what we want to do is navigate to the base class anytime you pass a derived class for this thing, right? So first, in this first example, you can see there's no modify proc, and we don't do that at all, right? So let's just show we're calling print position xy. Make sure it's working again, right? So we're calling print position xy on a royal and a peasant and a rect, right? Remember, the rect is in a totally different hierarchy. So what we get is royal is of type entity royal, right? We're getting that by we're assuming it's a struct, which is a little dangerous. Again, you would type check this if you were being careful. But we're assuming it's a struct, and we're saying, you know, that info gives us the name. We're also passing the string label that the user gave us, which is down here, and then we're printing out the position x and position y, right? So a royal is an entity royal, and a position is x and y, and a peasant is an entity peasant, and there's the position. Those are both 3 positions, and remember, these are our default values for vector 3. But the rect is a textured rect, and it's got a vector 2. So the code's working, but we don't necessarily like it, because we're calling different versions of this function for 3 different types, which means we're generating 3 different versions of the function, and that's no good, right? So just to show that, down here I'm baking it. I'm baking one for entity royal and baking one for entity peasant, and printing out the pointers to those 2 functions, and they are different. They are different. However, I define this function, go to basemost struct containing member, right? Which, let's just look at this whole thing as a little bit of a review, because I basically covered everything that you need in order to do this in the demo called, you know, runtime and compile time type information, but it's pretty quick, so let's look at it. So first, I'm calling this function getField. We're saying get a field, the field that we're looking for by name from this struct, and if it exists, just return that struct, right? So let's look at that part. Well, no, let's look at this. Okay, so we do that. If it exists and it's not imported from another struct, right, which is like if it's not a derived member, then return that. Otherwise, we're going to recurse into all the members of this struct and search for this thing by name in all those members, or if those members are not structs, if they're like floats or ints or something, just skip them. Then we know the members of struct, and then we recurse into here in that member. So we're recursively navigating down the class hierarchy. We could do the equivalent of multiple inheritance with this, etc., right? So let's look at getField for a second. It's pretty simple. We just say for everything in the members array of this info, if the strings match between the name, actually, I wrote this before I made string compare work with double equals. This could just say if it.name if it.name is equal to name, but I actually wrote a strings match at user level before I had that, and there that is. So anyway, this is doing a classic style string compare. Anyway, so if the names match, return it, otherwise return null, right? And here's hasField is built on getField, right? So we're just getField assumes we're a struct, and hasField says, well, maybe we're not a struct, and if we're not a struct, return false. Cast us a struct, and then do that stuff. And then is imported just checks this flag. And actually, I used this hack because I didn't have bitwise and when I wrote this, but I actually have bitwise and now, so we could have done that properly, but I didn't. Anyway, so let's go back to this. So this function is now, to nobody's surprise at this point, hopefully if you're following, going to be employed in our new version of print position xy. So now I've got a modify proc, and I'm just writing it inline again because I don't want to have too many names cross-referencing other things. So I've got some type t of whatever thing is, and it's a type info. And if it's not a struct, I'm going to give you an error myself, like, hey, you must pass a struct, and I'll return null so the compiler exits and complains. But assuming you gave me a struct, I'm going to go to the basemost struct containing the member, where I cast it to a struct because I know that's what it is, and I want the member position, right? Now, if you gave me something that doesn't have a position, I'm going to return null. Otherwise, I'm going to return the info member of the base class. Info is just I didn't do this to do. Like, I'm not sure why this autocasting. I should be able to return a derived class of info, but I couldn't. I had to like dereference it explicitly. So that's a minor compiler nit. But anyway, so I'm returning that. So the upshot of this, after this very long explanation, it's actually pretty simple if you just think about what it does straightforwardly. Now I can print position xy on a royal, and it's actually downcast to entity by the modify function, right? But it still works. I get a 3.1, 3.1. Peasant is downcasted to entity, so I get 3.0 to 3.1, which means, and we'll verify this going back to those diagnostics we had before, this means we're actually using the same code for both of these, whereas we wouldn't have been able to use the same code before, right? But we can also use that on any hierarchy, right? If that's all we wanted was to take an entity, we didn't have to be polymorphic at all. We could have just made a function that takes an entity, right? We want this to work on anything. So here's a screen rect and or a rect, which remember was a textured rect. That's what type it was. But textured rect is a subclass of screen rect or superclass. Which one is which? I don't know. I don't like object-oriented terminology. Anyway, derived class of screen rect. And so we've gone to the base class here, right? And that works. So let me turn on those diagnostics again. Let me make sure this still works. Demo, poly pre-build, and I'm going to turn back on the polymorph match. And let's look for what we want to see is line 895 is matched to line 894, right? So please work, please work. There we go. 895, polymorphic call matches 894. What you won't see is these matching. Except there's another point to make, right? Excuse me. So these won't match, right? So this is line 856, and that will not match 855, but you'll see it, 856 actually does match 860, right? And line 860 is this bake. So this bake, like baking a function and calling it do the same thing, and the bake gave us the same thing as the natural polymorph did, or whatever you would call it when you just call a function, right? But ideally, all four of these, this, and this would have done the same thing, but actually we got two different things. So the compiler does what it can, but you can help it out, in this case, by doing a modify. So I think that's pretty cool. That's something that I think is a very expressive thing, and to just be able to do that with everyday code is cool. All right, so now let's move on one step further than that, or one step more general. That was a very specific use case. But like I said earlier,
you.